Welcome to this explainer. Today, we're going to unpack the absolutely incredible internal and external forces that are continuously transforming our dynamic planet. Whenever we look out the window at a towering mountain, a deep, winding valley, or a vast, sweeping plain, it's really easy to think of the Earth's surface as permanent, unchanging, right? Well, the reality is far more colorful, violent, and honestly dramatic. Right beneath those peaceful landscapes is a world of unimaginable heat and crushing pressure. Our planet is essentially this massive, restless machine, constantly being sculpted and reshaped by immensely powerful natural forces. So let's explore exactly how this incredible process works.
Okay, let's jump right into our agenda. First, we'll look at Section 1, Inside the Earth's Engine. Then, we'll piece together Section 2, the Tectonic Plate Puzzle. Third, we'll explore boundaries, collide, pull, slide. Fourth, we'll see what goes into sculpting the surface. And finally, we'll wrap up with Section 5, Living on a Dynamic Planet.
All right, starting with Part 1, Inside the Earth's Engine.
To make sense of the mountains and valleys we see outside, we've got to look deep beneath our feet to understand the chaotic forces driving these changes. The Earth isn't just a solid, quiet ball of rock. Not at all. It's a wildly complex system of concentric layers from the crust all the way down to the core. Think of it kind of like a giant peach. You've got the thin outer skin, which is our crust, the thick, fleshy inside, representing the hot mantle, and finally the dense, heavy pit right at the center, which is the Earth's core. Every single one of these distinct zones plays a continuous role in the geologic drama playing out on the surface.
Now, what's really fascinating here is the sheer contrast in states, temperatures, and depths. Look at the crust. It varies wildly. It can be up to 40 kilometers thick beneath the massive continents, but just 5 kilometers thin under the deep oceans. Together with the rigid uppermost part of the mantle, this forms what we call the lithosphere. But just beneath that is the asthenosphere. This is an incredibly hot, mobile layer of semi-molten rock that behaves almost like warm, pliable plastic. It actually acts as a crucial lubricant for the entire planet. Below that, you've got the immense, mostly solid lower mantle, followed by a churning, fluid iron-nickel outer core. And finally, the inner core. A solid, spinning metal ball of blistering heat that literally rivals the surface of the sun itself.
Moving right along to Section 2, the Tectonic Plate Puzzle.
So, how does that incredibly hot, pliable layer we just talked about lead to the crust actually moving? Well, our surface is essentially a slow-motion puzzle made of giant, drifting pieces. The theory of plate tectonics, which was brought forward by scientists like W.J. Morgan, totally revolutionized how we view the globe. It tells us that the Earth's outer shell, the lithosphere, isn't one continuous, unbroken crust. Instead, it's fractured into massive and smaller slabs of solid rock. And because they sit right on top of that slippery, semi-molten asthenosphere, they aren't securely anchored down. They're basically continent-sized rafts of solid rock literally surfing atop a sea of slow-moving magma.
But you might be wondering, what is actually pushing millions of tons of solid rock? Picture a massive pot of thick soup violently boiling on a stove. Intense heat from the Earth's spinning core warms the molten material deep in the lower mantle, causing it to become less dense and rise up. As it reaches the cooler, upper layers right beneath the crust, it cools off, gets heavier, and sinks back down into the inferno. This continuous loop takes millions of years, creating colossal convection currents. It acts just like a planetary conveyor belt, literally dragging those gigantic tectonic plates a few centimeters every single year.
Now, these distinct types of massive solid rock slabs are what carry the oceans and continents across the globe. We aren't just talking about patches of dirt. These are colossal structures. Take the Pacific Plate, for example. It's almost entirely submerged, incredibly dense, and carries the crushing weight of an entire ocean. Contrast that with the Eurasian Plate, which proudly holds up the bulk of 2 massive land continents. Some plates are strictly continental, others oceanic, and many are just a mixed bag, carrying both land and sea as they blindly navigate the globe.
Okay, Section 3, Boundaries, Collide, Pull, Slide. This is honestly the most dramatic part of our story. What happens when these massive, slow-moving plates finally meet at their edges? At a convergent boundary, 2 plates move directly towards each other. If it's 2 massive continental plates colliding, the rock has nowhere to go but up. It buckles, warps, and folds under sheer, unimaginable force, pushing solid rock thousands of meters into the sky.
This is exactly how the magnificent Himalayas were violently thrust upward. On the other hand, if a dense oceanic plate meets a lighter continental plate, the heavy oceanic crust gets dragged deep into the inferno of the hot mantle in a process called subduction. This ultimately melts the rock and sparks violently explosive volcanic eruptions on the surface above.
Conversely, when plates pull apart, they give birth to brand new crust. This is called a divergent boundary. As the giant plates slowly separate, a massive rift opens up, and highly pressurized hot magma from the mantle rushes up to fill the void. Picture a giant underwater zipper opening up along the ocean floor. As that bleeding magma hits the icy pressurized ocean water, it instantly flash freezes and hardens. This builds towering underwater mountain ranges, like the immense Mid-Atlantic Ridge. So the Earth is continuously growing a brand new rocky skin in these expansive zones.
And then, when plates decide to grind past each other without creating or destroying crust, we get a transform boundary. Think of two incredibly rough blocks of sandpaper being forcefully pushed together and trying to slide past one another. The friction is astronomical. The rock literally bends and deforms under the immense tension over decades or even centuries. Then, snap. The rocks violently break and slip past each other, releasing all that stored pent-up energy in an instant. This sudden release sends massive shock waves rippling through the crust, violently shaking the ground as an earthquake. The famous San Andreas Fault is a prime example of this intense, terrifying horizontal grinding.
All of these volatile interactions perfectly map out to the infamous Ring of Fire, a highly active zone wrapping right around the Pacific Ocean. Because the immense Pacific Plate is constantly colliding, pulling, and sliding against several other plates all around its edges, it's created a massive, horseshoe-shaped ring of absolute chaos. The sheer volume of energy released here makes this single zone responsible for the vast majority of the world's most devastating, city-leveling earthquakes and explosive volcanic eruptions.
Let's dive into Section 4, Sculpting the Surface.
While the Earth's internal engine and tectonic plates build the world up, a whole different set of forces is relentlessly trying to tear it back down. What we're witnessing is an eternal geological tug-of-war. You have the internal forces pushing the Earth up and the external forces wearing it right back down to sea level. Internal forces, like the violent folding, faulting, and dramatic volcanic eruptions we just explored, are the builders. They thrust mountains into the clouds. But the very second a new landform is pushed up, external forces begin to attack it. It's this striking contrast between violent, sudden construction from below and the slow, patient dismantling by wind and rain from above, gradually reshaping rugged peaks into smooth plains, rolling hills, and deep valleys.
Now, it's really vital to clarify a common mix-up between two distinct external forces that work in tandem: weathering and erosion. Weathering is the process of weakening and breaking rocks right where they sit. Actually, picture microscopic plant roots physically prying massive boulders apart over decades, or acidic rain slowly dissolving solid limestone. The rock breaks, but it stays put. Erosion, however, is the actual transportation network. It's the physical movement of that broken, weathered material from one location to another. To put it simply, weathering breaks it, erosion takes it.
These specific natural agents of gradation are the tireless artists carving out the incredibly diverse valleys, caves, plains, and cliffs we see today. Running water in rivers acts like a liquid blade, slicing through solid rock plateaus over millennia to leave behind jaw-dropping monuments like the Grand Canyon. High winds in arid deserts act as nature's sandblaster, whipping grit against rock formations to sculpt them into bizarre alien shapes. Massive glaciers behave like slow-motion rivers of ice, acting as continental bulldozers that scrape, crush, and gouge out entire U-shaped valleys. And finally, coastal sea waves act as relentless battering rams, tirelessly pounding the shorelines, wearing down towering cliffs, and depositing pulverized rock to build our sandy beaches.
Which brings us to our final part, Section 5, Living on a Dynamic Planet. We aren't just passive observers of these immense geological processes. Our entire human civilization is fundamentally shaped by them. Understanding this explainer isn't just about categorizing rocks. It's about predicting hazards, uncovering hidden resources, and surviving alongside the immense, indifferent power of nature. The varied landforms created by these forces completely dictate our local climates. Think about it. Volcanic ash from destructive eruptions actually creates some of the most incredibly fertile soils on Earth, drawing generations of farmers right to the edge of danger zones. Ancient fault lines dictate where we find vital underground aquifers and massive veins of precious metals today. They influence where we build our sprawling cities and how our cultures historically developed. But living on this machine means we must be vigilant. Steep mountains are constantly prone to sudden, catastrophic landslides, while arid plains can whip up blinding sandstorms. We are inextricably linked to the physical shape of the Earth's surface.
Thank you so much for joining this explainer. As you step outside today, look closely at the landscape around you and ponder this. Are those gentle, rolling hills you see actually the worn-down nubs of ancient, towering mountains that once rivaled the Himalayas? Is that nearby river slowly carrying your hometown down to the sea, grain by tiny grain? Our planet is vibrantly alive, continuously destroying and rebuilding itself right beneath our feet. Keep your eyes open to the incredible, dynamic world outside your door. Until next time, stay curious.